Today we're going to talk about elements and isotopes. This is our second learning target for Unit 2, so learning target 2.2. Today we're going to really talk about the composition of atoms, so the nucleus versus the electrons, and then the types of information that the periodic can tell us that help us to, that give us some more information about the element's composition. So how do we distinguish between atoms of different elements? And really the important thing here is going to be protons. So protons are super important. So elements are composed of atoms with different numbers of protons. So different atoms are going to have different numbers of protons, and that number is going to be associated with the atomic number on the periodic table. And it's really protons, the number of protons, that determines the identity of that atom. So every single lithium atom, let's say the blue particles here are in my nucleus, those are protons. Every single lithium atom is going to have 1, 2, 3 protons. Every single carbon atom is going to have 1, 2, 3, 4, 5, 6 protons. And those protons are really going to be the identifying characteristic that causes an element to be lithium or causes an element to be carbon. So it's those protons, they're really, really important. And those are how we kind of define or determine the element's name and what it is. When we look at the periodic table, if we look at just the square, so here I have just one of the squares for the element carbon on the periodic table, we get a lot more information than you might think. So the letter is giving me the symbol, the element symbol. I'm always going to be giving you guys periodic tables to use that have the names as well. So there's the names up at the top. This number above the symbol, this is the atomic number, and the atomic number is also telling me the number of protons. We'll talk more about this in a minute. So this atomic number is the number of protons. That's my identifying number for that particular element. And then this bottom number underneath the symbol, this is the atomic mass, and really the average atomic mass. So this is telling me the average mass of all of the atoms of carbon if we were to take a sample of carbon atoms from Earth. So it's the average mass of all of those atoms that they would find in a sample. And then elements, they're listed in increasing order based on atomic number. So that also means that they're listed in increasing number based on the number of protons that each atom has. So when we're looking at the names and symbols of elements, there's some rules that are associated here. So the symbol is either a 1 or 2 letter abbreviation for the name. And it's important here that if it's just a 1 letter abbreviation, like here we see carbon, the single letter abbreviation is capital C, that letter should always be capitalized. And if it's a 2 letter abbreviation, like we see here with magnesium, the first letter should be capitalized and the second letter should be lowercase. An example of why this rule is important is if we look at, let's say, carbon and oxygen. We're going to have carbon is going to be a capital C, oxygen is going to be a capital O when we are writing them. CO is carbon monoxide, that's a compound. But if we look at the periodic table, capital C lowercase o is an element cobalt. So this is carbon monoxide, this is cobalt. So it's important, especially when we have those 2 letter abbreviations, that that second letter should always be lowercase. Some of the names that we see for elements on the periodic table or some of the symbols might look a little weird, and the reason for that is because the original names came from Greek or Latin origins. So when they created these symbols, to avoid a lot of elements having very similar looking, or even elements that started with the English names had the same first few letters, they go to the Greek or Latin name to develop the symbol. And some of these we're going to be using quite a bit. So it's important that you are kind of familiar with this. So gold is AU, lead is PB for plumbum, which was that original Greek Latin name. Sodium is Na. This is one that we use a lot in this class. So this one's really important. Iron is Fe. So these are just things to pay attention to when you're looking for these elements on the periodic table. At being familiar with some of these kind of oddball symbols could be kind of helpful for you. So now if we look at the general structure, and we should be familiar with this from the activity, as well as from former science classes that you had even in elementary school and middle school. So here we have the nucleus in the center of my atom, and in the nucleus I have positively charged protons and I have neutral neutrons. Okay, so protons positive, neutrons are neutral. And then we have our electrons, our negatively charged electrons orbiting around the outside. And we're mostly going to be using this model where we see electrons in orbit around the outside. So we have those negatively charged electrons. So you guys are going to have to be able to identify the number of protons, the number of neutrons, and the number of electrons based on only partial information and then knowing some of the information from elements from the periodic table. You do not need to memorize the periodic table. I will always give it for you to use as a reference because that is what it is intended for. So here, if we're looking for the number of protons, if I'm asking you how many protons does an atom have, here you're going to be trying to find the atomic number of that element. So for example, for let's say fluorine, if we look for fluorine on the periodic table, it has the atomic number of 9, which means it has 9 protons. Okay, atomic mass. So this is the, like I said earlier, this is the average mass of all of the naturally occurring isotopes of an element. We're going to talk more about this term isotopes here in a minute, but it's the average mass of all of the atoms of that element that we find on Earth. And we look at that average. So this is that number that we see on the periodic table. This is slightly different from a mass number, which we see here. So mass number, this is going to be the mass for a specific atom of that element. And I say here, it can be rounded from the atomic mass or calculated. We are not typically going to be rounding it from atomic mass, so don't write that down. You can, however, calculate this, and we calculate by adding the number of protons to the number of neutrons. And really, when we're looking at the mass of an atom, it's measured in AMU, which stands for atomic mass units. So atomic mass units is how I measure the mass at an atomic scale. So if I say the mass of an atom is 12, I'm talking about 12 AMU or 12 atomic mass units. So here, one proton will have a mass of 1 AMU, one neutron will have a mass of 1 AMU also. Electrons have such a small mass that we don't actually include them when we look at the mass that we're calculating for atoms on the periodic table, because even the largest atoms that have the most electrons, that electron still doesn't come anything close to 1 AMU. So we don't include the mass of electrons here. So for the mass number, it's the number of protons. Each one has a mass of 1. Plus the number of neutrons, each one has a mass of 1. This is really useful because if I have the mass number and I have the number of protons, which I get from this atomic number, then I can very easily calculate the number of neutrons present in an atom. So let's say, for example, we have our fluorine again. So let's say this particular atom of fluorine has a mass number of 19 AMU, atomic mass units. I know that fluorine on the periodic table, its atomic number is 9, which means it has 9 protons. Okay, that's a 9 protons. So here, if protons plus neutrons equals my mass, I can go ahead and subtract my protons away from my mass, and then it will give me only the number of neutrons. So I'm going to go ahead and take my 19, which is my mass number, minus the 9 protons, and that gives me 10. So now I know that I have 10 neutrons in this particular atom of fluorine. So if you have the mass number and the number of protons, you can calculate neutrons, or if you have the number of protons and the number of neutrons, you can calculate the mass number. Either way. Typically, protons is going to be a number that you're always given because it's going to be the identity of the atom. All right, and then finally, the number of electrons. This is going to be typically equal to the number of protons, but it's only equal to the number of protons in a neutral atom. So let's use fluorine again for our example. I have fluorine, and fluorine has, what do we say, 9 protons. If fluorine is neutral, that means that it has an equal number of positive and negative charges. So my protons are positive. If I have 9 positively charged protons, that means I also need to have 9 negatively charged electrons. And a symbol we use for electrons is lowercase e with a little minus on the top right-hand corner. So 9 electrons there as well. But now let's say I have fluorine that has a positive 1 charge. So we put our charge on the top right-hand corner. So fluorine with a positive 1 charge, that means I have 1 extra proton. Then I have electrons. Remember, the proton number can't change, but the electron number can. So instead of having 9 electrons, this fluorine atom would only have 8 electrons. And let's say I had fluorine that had a negative 1 charge. Fluorine with a negative 1 charge, instead of having 9 electrons, there would be 1 extra negatively charged particle. So here I would have 10 electrons. So there would be 1 extra electron over the number of protons. Isotopes, and we saw this on this word on the last slide. So an isotope is an atom of the same element that has a different mass. And we also said that all atoms of the same element, they have to have the same number of protons, and electrons don't have enough mass to really to be calculated in with the mass of the atoms. So if we can't change the number of protons and changing the number of electrons doesn't really change the mass, that means what makes these isotopes different from one another is the number of neutrons. So here are 3 isotopes of oxygen down below. So here, each oxygen, notice how each oxygen has the same number of protons. They all have 8 protons. They have to have 8 protons. These are all neutral oxygen atoms, which also means that if you count the electrons that are orbiting around the outside, they will also have 8 electrons. But each isotope of oxygen has a different number of neutrons. So this oxygen isotope, so here it's oxygen with a mass number of 16, has 8 neutrons. This oxygen isotope with a mass number of 17 has 9 neutrons. And this oxygen isotope that has a mass number of 18 has 10 neutrons. So it's the number of neutrons that changes here. And we saw this on the last slide as well. There's a specific type of notation that we use when we are looking at the mass numbers of isotopes. So I can write this in a couple of different ways. I can either write the name or the symbol and then a dash and then the mass number. So this is my mass number for that particular isotope. Or I can put the mass number on the top left-hand corner of my symbol. So those are both ways to write this. So let's say I have fluorine with a mass of 19. I can write F-19, or I can put 19 up in the top left-hand corner of my symbol F there as well. Valence electrons, this is another term that you guys are going to need to be familiar with going forward in this class. And really, valence electrons is what we're going to spend a majority of the school year talking about, because these are the electrons that are doing the interacting with the environment. So here, electrons, they occupy different energy levels within the atom. So we have these lower energy level electrons. We have this next loop of electrons is the next highest energy level. And the outer electrons, or the outer energy level electrons, these are known as valence electrons. These are going to be the ones that are able to make bonds with other atoms. So these electrons are really, really important. And we're going to talk more when we talk about the trends that we see on the periodic table, how we determine how many valence electrons an atom has. Based on how many valence electrons atoms have, that determines really how they're bonding. So all of the chemistry that we're going to be studying in this class really has everything to do with these valence electrons and what exactly they're doing. All right, guys, if you have any questions, go ahead and leave them at the end of the video, and we'll chat tomorrow.